Hello and welcome everyone. So in the previous session we have been discussing about backpropagation, and now we'll take the session from there. So if you see, the first step that we had done was we had to do forward pass in the network. If you have a network in which we have input, hidden layers and output, and we do a forward pass, and by now you should be very well versed with the forward pass. And we did two things. So we said there is this vector method and there is this element wise form. So element wise form and vector method. So these are two things that we were analyzing. So you can also perform backpropagation and you can also perform forward pass in both of these ways. So element wise form, it usually gives you better intuitions because you take one element into consideration and then you do all the analysis on that. In the vector form, then you club all these things and then you take advantage of things like broadcasting and stuff like that, which we have discussed in Matplotlib, which I discussed I think in pandas, numpy and other libraries. So this vector form takes advantage of that. So okay, just to revise you how is forward pass done, if you have, and you know the notation, I won't again come with the notation. So now you know that AI, so this is the pre-activation function, let's suppose of kth layer. So I means the one element of that. If you have that layer, if you can imagine, you have, let's suppose, some layer, some kth layer is there, and then you can see in that layer you have AI, that is pre-activation, or we can call this affine transformation. So this is the one element of that, that is a vector. If you see, that is a vector, so that vector is called as AK. If you take AKI, that means one element of that vector. So this was equal to, when we previously saw how to compute this, so this was equal to J1 to N. So you fix this I. So you say we have in this bigger matrix, let's suppose this W key is the bigger matrix. So in that you fix that row number, I number, and then that is, it is at the K, and then you navigate over J. You had these I1, I2, I3, I4, and this is Wij, J, and then K. So this is H, J, K minus 1. Again, if you see, Hk is the whole vector, and then if you want to take one point, that is this Hj, plus again bias Bk is the vector, and when you want to take one value, so you take this index k. So this was the first step when you aggregate this. So this is the aggregation or non-linearity or the affine transformation. And after this, on this you apply some activation function to get activated input. So you have h of k, so this is the whole vector again, and then if you want one element, so you'll index it with I, and then what you'll do is you'll apply some activation onto this, so on this AIK. So this thing over here was in the vector form. Okay, so this was, no sorry, this was element wise. So this over here, if you see, was element wise form. I hope the people who were present in the last session, or who have watched the recording again, so these people will be able to understand this. Now in order to convert this directly into vector form, so what we can do is we can directly take this, AK is equal to WK, and then this H K minus 1 plus BK, okay, and then HK, this is equal to some F of AK, and F over here is activation function. So this over here is the vector form. This is how we perform the forward pass. So when you perform the forward pass, now you have inputs. You know how inputs are. Input H naught is equal to X, so this is the input because it's the input layer, and if I take H naught of I, that is Xi, suppose, so that is the feature, ith feature of that input, okay. So and HL, this is the output. So when you have the last layer or the lth layer, lth hidden layer, so that is your predicted output. So this is your prediction and this is your input. This was just to revise what we have done. So in order to do the backpropagation, and we had a lot of discussion how this is, we made some computational graphs and stuff like that, and we wanted to see that, we wanted to find somehow this. So we had this loss function and we wanted to find how is it dependent on these parameters. If we nudge some parameters, how will the loss function behave? So if we nudge, let's suppose W1, W2, bias 1, bias 2, so what is the impact on the loss function? And if we nudge in that particular direction, so what is the loss, what will happen to the loss? And we want to decrease the loss. So that's what we wanted to do. Okay, and then once we know the direction of these different derivatives, and we will nudge these vectors into opposite of the ascent. Basically, when we compute the gradient, and you know that the direction that you get is the steepest ascent, and you want to descend the function, and you will take the negative sign of that, and that we have discussed in gradient descent. Okay, now we'll define a vector which we can call as error. Before defining error, I'll tell you one more thing. So you have this loss. So how is this loss constructed? Now let's go backwards. So you have this loss. So this loss is basically constructed by two things. You get some ground truth, okay, and you get some prediction. So y hat. So how do you get this prediction? Let's suppose if we work on the last layer, if we get this last layer, so you get this from HL. Okay, how do you get this HL? So you get this HL from applying activation function. You apply activation function on AL. How do you get this AL? You get this AL from three things. This is what you should remember. The first thing, you get it from a weight matrix WL. You get it from a previous activation L minus 1, and you have biased L. This is at the last layer. This is what is happening at the last layer. If I change this or this value, okay, so there will be some issue will be, so we'll have this loss function. So let's consider this loss now. So this over here, this is a single node and we can call it loss. Okay, you cannot change this, okay, and this is an output of this is an output of this, and this is output of this. And again you can construct this graph again. So what is this HL coming, what is this HL coming from? So this WL is fixed, this BL is, like, these are the parameters. This is coming from the activation. So you have to write A L minus 1. So this is where it's coming from. So where is this AL coming from? So it's coming from three things. It's coming from W L minus 1, it's coming from H L minus 2, and it is coming from B L. So is this graph clear? The graph I am making over here. So if you understood this graph, so you see it from here. I'll take questions in a while, just let me clear this. So I have this. So if I have my last layer, so this is my HL. So I take something, I do something to this, and I get my prediction, and I compare that prediction with the original thing I have, ground truth I have, and I compute loss based on that. And my thing is I want to do something with this loss. So this loss I want to minimize. I want to get less loss of this. So I'm asking, okay, how to minimize this loss? I should do something with the prediction, but prediction is based on the last output, whatever I got at the last layer. Okay, that is based on whatever I had the activation, the pre-activation at that layer. Okay, that pre-activation is dependent on previous elements 1 layer's activation, its weights and biases, and this is how it goes on till I go to the input. Okay, and now I can do something with these. I can do something with this. I can do something with this. I can do something with these and these. If I nudge these somehow, and I can have control over this loss, so I can decrease the loss. Okay, I need to compute gradients of these things. I can compute it element wise, and then I'll also show you the vector representation of these things. I'll take questions now, please. So if you understood this, the one major question is that why is it called back propagation? So what do we do, or why is it called backward pass? So in this, if you see, if let's suppose you have to compute effect of this WL minus 1, you have some weight. Let's suppose that belongs to some previous layer, and you have to compute, if I nudge that weight, if I nudge those weights, what will be the impact of this loss? So in order to do that, you have to perform all the computation that is in front of that. So to clarify this, so let's go to the neural network. If you see this over here, so if you have to compute what is the effect of this weight on the loss function, you have to compute the gradient with respect to this. You have to compute dou L by dou W1. So for that, you first have to compute this, and then you have to store it somewhere. You have to compute everything that comes in between, or that comes after it, that comes after this. So once you have all these values, then because of chain rule, you'll use all these values and to compute this. Okay, that's why it's called backward pass, because in order to do that, you'll have to have all the values of this first. In order to compute, let's suppose in order to compute this, so you'll have to compute the value with respect to this weight, value with respect to this prediction. You'll have HL over here. So this will be computed with respect to this, then with this weight, then with the bias of this, then with this HL minus 1, then this with A2, and then this with weight, and finally you can go to the point where we are at. Basically, you come from the forward, you come from forward thing. So whatever you are currently at, so all the things that are coming after that, those should be computed, and then only you can compute the effect of that particular weight or that particular node with respect to the loss function. So that's why it's called backward pass. So in a nutshell, it's called a backward pass or back propagation, because anything that is coming ahead of that, you should compute that first in order to compute the effect of a loss function which is into consideration. In order to compute this dl by d11, you should compute everything that comes in the forward of this. So you should compute dl divided by, let's suppose, al, or for that sake hl first, then this hl by al, then this dou al by dou hl minus 1, something of this sort. So you should keep on doing that till you reach this w11. All these things come after, so they come after w111, so they come after this. So whatever comes after a particular weight or a bias, or after a particular function, so all of these things should be computed and cached properly in order to use the language of dynamic programming. So you'll store it somewhere, so as, because these things will be reused a lot of times, so you'll have to reuse these things. So whatever comes after a thing, all these things should be stored in order to compute the gradient of a particular thing. So that's why it's called back propagation or backward pass. Okay, so now coming again, if you understood this thing, if you understood this is the this is called, so this thing over here, whatever I'm making so far, these are called, these all are called computational graphs. Now I'll introduce a term which is called as error. So let me introduce a term which is called as error in order to make this computation pretty easy. So I'll introduce error del I of k. So this is basically telling you error at kth layer, okay, for a particular neuron I. So what is the error there? So what can I do that? So this is defined as dou L loss function. Take that loss function and take its derivative with respect to this ai of k, because you know ai is the aggregation one and you know how it is defined. So you know how this ai is defined. So this is element wise. So this is element wise. So this is element wise error. If I have a neuron at a particular one and I am defining error at a particular point, because you know that this ai is one of the activation, is one of the aggregations at one of the neuron. This is for a particular neuron. If I have to do it for a whole layer, so how I can do that? I can define this is an error at a layer. So error, this is error at a neuron. So this is error at a particular neuron. So this is error at a layer. Error at a layer. So this is error of neuron I in the kth layer. So you have kth layer, there is some neuron I. So this is how I am defining error. So dou L by dou ai. Basically take a differential of L with respect to that aggregation at that particular neuron, because neuron has two things if you remember. So neuron has ai neuron basically means it will be aggregated here, this is at kth layer, okay, and then you apply activation on this, so you will get hk, so you will get hik. So this is after you apply the activation on this. So when you have multiple of these neurons, so you get a layer. So this del ak I can write directly dou L divided by dou a of k. So this over here, this will be gradient. So this will be gradient. Gradient is a set of vectors. It will be of there will be a lot of vectors. This will be a single derivative. So this is a derivative. Okay, set of these derivatives where they form a vector. This is the gradient. So if you understood this is pretty easy. So this is the element wise error. So if you have to read this, so I'm just introducing a notation. So del I of k means the error at ith neuron, which is in the kth layer. Okay, so what is that? You take the derivative of loss function with respect to ai, with respect to the affine transformation or linear combination of that neuron in the kth layer. Okay, so this is how I introduce this. If I now have to compute what is the final error, so I'll compute final error. So error at final layer, error, final error, I can compute like this, final error. If you understood this terminology. So if I have to do element wise, so how I can do that? So I'll say del I of L. So because L is my final layer. So how I can do that? This is dou L divided by dou. Now I'll bring that hi, because if you know how to compute ai, so see this layer, see the last layer, see this neural network. So you have, let's suppose this, so you have hl, but this hl basically you have this al. Suppose you have al. So in this, suppose you have final neuron, final layer is this. I can write that because I don't need this diagram even. I hope you can understand this. So I have final layer. So let's suppose these are neurons in the final layer. So in this final layer, I'll have output HL, and based on which I got my expected output or the desired output that I want, predicted output. But this HL, I got it because of AI. So this, if you see this, so I got it because we had pre-activation before that. So I had this AL. So AL once applied with the activation, I got HL because of that. Okay, so that's what I'm doing here. If I have to compute this del I, so I showed you this. So if you see, so this is how I defined it. Now I have to compute final error, so I'm doing it element wise. So I'm saying take this di by dl, but I got this hi because of ai. So how to do this? So del I by h, I'll introduce this h in between. So and then I'll take derivative of this. I'll see f dash of ai at lth layer. This is because of chain rule. How many of you remember this? So if you see this, what is the meaning of this? So I introduced this notation basically. So this was equal to, I had to compute, so this over here dou L by dou A I lth layer. So but how did I get this? Okay, how did I reach this? How did I reach this AI? If I have to compute this, I have to see this. I got, so this was used in performing activation, and then I got this activated, I got the activate value. So I'll compute like this. I'll say dou L by dou H I of k. Okay, and then I applied some, how did I get this? Because I applied some activation function on this. So I have to take activation function, derivative of that activation. This function is activation, is the last layer. So you have HL, so you applied some activation and you got some output. So I want to see, because of that you computed loss. So I'm saying what is the derivative of loss function with respect to this AI? So but in order to reach AI, I went through this HL. So everything should be imagined by now. So this over here you can write it AI of L. Okay, so now I replace this with delta. So this was delta over here. That's how I introduced the notation I introduced over here. So this was del I. So this is the element wise. So if I have to write it in vector form, pretty easy now. So I can do it, I can do the whole thing in once. So this was in terms of in terms of elements. If I have to do it in vector terms, so I can write it over here. So this was element wise. So vector wise will be something of this sort. So this whole thing was element wise. And if I have to do in the vector notation, so whole of this WR, error at lth layer. So this was error with respect to one neuron, ith neuron in the lth layer. Okay, and this is error with respect to the last layer, the whole layer. So how I can do that? I can compute dou L by dou whole of this HL. Compute this loss function with this, and then I'll say derivative of A with respect to all of this. So this will be just one value. This will be derivative. So this will be a gradient. So you should be remembering this. So this will be a vector. Okay. So this will be vector, basically gradient, vector of derivatives. That's what we call gradient. So this over here will be a derivative, and over here. So what do you do? You will generally see a dot written like this, and this is called as Hadamard multiplication. This you will get a vector out of this. So you'll get a vector out of this. So this was single value. Okay, this over here also was a single value because this was element wise activation. So you will also get a single value. This was element wise, and now this is vector based or vector form. This is error at lth layer. How to compute that? Take loss function and compute its derivative with respect to all these HKs. Okay, and then take this AL, basically the affine transformation at lth layer, and apply activation over all these units. So this will be a vector, this will be a vector, and you perform Hadamard multiplication to get again another vector. Is it clear? Is it clear so far? Okay, and here now loss functions can be different. So I can have loss functions can be, let's suppose, mean squared error loss. Okay, I can have loss functions as binary cross entropy loss. I can have different loss functions, and I can have different activation functions. So these are different loss functions can be there, and different activation functions can be there. Activation functions can be sigmoid. Activation functions can be ReLU. Activation functions can be Swiglu. A lot of activation functions can be there, and that is why we need differentiable loss and differentiable activation functions. We prefer those. Why? Because you saw that we are using differential everywhere. We are using differential here. We are using differential here. Okay, in order to do this, if you understood this, again, I'll just wrap it up and then we'll do the rest of maths maybe in the next class. So I'll again wrap it up. So what I'm telling you, if you have some loss function over here, you had some loss, and this loss was dependent on some neurons, let's suppose, some neurons over here. So you said, in order to compute something of this, you'll take derivative of this. Let's suppose we chose a neuron in the middle of a network. So we said, in order to do, how can I nudge the value of this? I have weight of this, and because of that, I get affine transformation. I get, let's suppose this is at kth layer, I get AK. And after applying this, I get h of k. I get activation of this. And now I want to compute some derivative. I want to see dou L by dou AK. How is this nudging of this impacting these values? Okay. So what I'm trying to tell you is, so you basically follow this whole path and you see what are all things that are impacting it. So what are the things that come forwarded? So you use chain rule and go all of these things till that, and at the end you use this. Basically, you are using dou L by whatever is here. So dou H L initially multiplied by dou HL divided by dou HL minus 1, or AL multiplied by dou AL divided by dou HL minus 1, and you keep on going till you reach this value, this particular value. Okay, and you do this by using the chain rule. Okay, if you understood this. So as I said, now you might have different loss functions and you will have to take different loss. Let me just take some MSE loss. Let's suppose we have this mean square loss. Okay, so what to do if loss is like this? If loss is, you might have heard loss, mean square loss sometimes is written like this: y minus y bar whole square. This is how loss can be predicted. So if you have to compute this, you will compute dou L by dou, let's suppose, HL. This is at the lth layer. So how to do that? So you'll say this will be equal to, so if you just compute this, you'll get HL minus y. This is what you will get. We compute this at your leisure time, you will get this. Okay, if let's suppose you have to compute this dou L now. So what is the error at that? So you'll say, okay, I now know this. So this error is, I now know this. I also have to, I have somewhat, I also can get to know what activation function I use. So I can use, if it is a loss function, I can use HL minus y and then Hadamard of whatever activation function I use, the derivative of that activation function with respect to AL. This is how we can compute the error. Okay, we compute the derivative with respect to L and then derivative of that activation function. Okay, and similarly, let's suppose if we have softmax or cross entropy, same thing can be done. So in shortcut, you can only get this. So dou L will be HL minus y. So in terms of, this is MSE in MSE. So in cross entropy, you will get this. and then you will have, this is for the lth layer, so we did it, this is for final output, this is for final, basically the last layer, lth layer. So now you will have to do same things with L minus 1 comma L minus 2. You'll have to do all these layers. You have to somehow understand all of these things in order to do this. Now you have to repeatedly perform this. You'll basically compute now this. You'll compute delta I of k. Okay, you'll have to compute the error, and based on that you will do it. You'll do it for all the layers. This k can now take values from L minus 1 till the last layer. Let's suppose till first layer, till the first hidden layer, and input is fixed. Okay, if you can do this. So this is the last step in backpropagation. Last step, I'm leaving this last step for you people, if you can, because I told you what's happening at lth layer. Okay, what will happen at L minus 1 layer, what will happen at that layer, you have to do it. And this last step, if you understood this, you'll be easily able to grasp this thing. But you saw that how important is chain rule. So how important chain rule is, and how important is to compute these gradients in an effective manner. As I said, backpropagation was not possible. Why? Because we have to backpropagate. It takes a lot of time. You see, if you have now, let's suppose 1 million nodes or 1 million weights, you have to compute gradient for 1 million things. Okay, for just one single data point. If you have, let's suppose, million weights, if you have 1 million weights and biases. Okay, and you have one data point. So for one data point, with respect to that, you will compute 1 million, because based on that data point, you will compute 1 million gradient, 1 million derivatives, basically a gradient vector which will contain 1 million, and you will have to perform gradient descent. Previously also, as I said, so we will only use, if you have now 100 million points and you have 1 million parameters, then if you use all the points to compute gradient, you multiply this, so this will be let's suppose 100 million to 1 million probably is like a billion, so we'll say we need 1 billion computations to do this. That's why we do mini batch, so we'll take some smaller batch. We defined an error vector. Okay, we defined a vector that's called error at layer k. So how do we define that? We said, let's call this a delta k. We'll take one element in there. Let's suppose if we have some neural network of this sort. So this is, let's say, one layer. I'll not make neurons, I'll rather make layer like this. Okay, suppose this is your output neurons and this is your input. Suppose and these are filled with neurons. You can consider something of this sort. If I take any layer, let's suppose I'll take this layer, kth layer. Okay, so if I take a layer of this, and I'll define some error function. So how I will define this error? So I'll define it like this. So this error function is equal to L by dou aik, and you know that on this function you will have this pre-activation. Pre-activation is ai. So this is element wise. So here I am saying it element wise. So actually, if you see, I can write it in vector form like this: delta k. So this is dou L by dou ak. So basically, I am taking derivative of all these elements with respect to each of this. So you know that this will be a vector. So this will be some vector of errors. So vector of error 1, error 2, error 3, and so on. Okay, if I talk about this k vector, so this is how I define it. Okay, so now we started with the last layer. If you remember the last lecture, we said let's say if I start from the lth layer, so basically from final layer, lth layer. So that is our final layer. People who have watched the previous lecture, they will be understanding all the things that I am saying, and people who have not seen the previous videos, they might be having a bit of difficulty. So if you have this, let's suppose this is your lth layer. So I am now defining it like this. So this is your lth. So how can I define it? So this basically is equal to dou L divided by dou. Here if you see, this was kth layer. Now I'll define it as ai of k. This is how I'll define it. So this is the definition by definition. And now I can explain it like this. So dou I by L. So if you see the last layer, so last layer, how can I compute? Because after that I applied some activation function onto that. So whatever activation function I applied, the output activation function, I'll have to take derivative. But so by chain rule, so what will happen is I'll get value of this sort. I'll get dl by dhl, basically previous layer. So if you see the last layer, if you see last layer neurons, so here hl is the output or the prediction, and then you apply loss on this. So you let's suppose if you use mean square error or something else, so you apply something on this and you get loss. And the first thing, if you have to compute the derivative with respect to, if you have to compute with respect to a1, al is right here. Al is just before the last layer, or you can say pre-activation of the last layer. Pre-activation of the last layer is al, and activation, after applying the activation, you get hl. So you have now these two things. Once you want to compute this, you want to compute dou L by dou ai. So that is, you want to compute how is this loss function impacted by the pre-activation values, this aik. Okay, so how I can compute that? So first, you know that this is connected by this. So if I can make this, so this L is loss is connected by this is connected by this. Basically, it is impacted by these things. So we will first take derivative of this loss function with respect to this HL, and then we will take the derivative of this HL, and so rather than doing it again, so you know that this dou L divided by dou A, let's suppose AI, so this should be rather L minus 1. If I write it correctly, this is A, let me just see it. So this is kth, and if we have to define it for this, so this will be at L, because I want to see for the previous value. So now you have this, so this is what we have to compute. So this is dou H, so this is dou HL by dou A, and now this is how we compute it. And you know that H function, it is somewhere you have this activation function and all this stuff, so I can replace this like this. So I can compute this and I can replace this, because I have to take derivative. I can say this is f of AL. Okay, that's what actually happened. So what you did is, so you took that HL. So how do you got HL? So you got HL by applying activation function on AL. So you had this AL, you applied activation function on that. Okay, now in order, by the help of chain rule, so when I wrote DL by, let's suppose, DHL, so what is the meaning of that? DHL by DAL. So this means if I nudge this AL value, how is this HL impacted? So I said, how do we got this HL? So this HL, we got it because we computed it from, we applied activation on this. So we applied activation on this f of AL. So we can just take derivative like this. Okay, so this is this is notation, and here if you see this, so this is the vector notation of this. So if I want to show it element wise, so how it will look element wise is like say this. So dou I of L. So this is delta I. So delta I at L. So basically the error at the Lth layer. So now you just focus on one neuron. So here we were focusing on all the layers. So now if you focus on just one neuron, so I'll make it a bit cleaner over here. So if you see, these 3 neurons are here. So now I'll have some activation over this. So here, let's suppose for this neuron, let's suppose consider this is ith neuron. So I'll say AI of L. That means pre-activation of ith neuron at Lth layer. So we have this L. So after applying activation function on this, so what you will get HI of L. So you activated this, you applied activation on this, and you got this. Okay, if I now apply, if I have to compute this del of I, and you know what is this equal to? This is equal to loss function with respect to AI of L, with respect to this. But you know how it comes from? It comes from L goes through this, and then it goes through this. But basically, L is getting impacted by this, and this is getting impacted by this. So by help of chain rule, how can we write it? So basically, what we have to compute is dou L by dou AIL. So this is what we have to compute with respect to this one element. And so what is this equal to? So delta of L is equal, so dou L by dou AI. So now we'll start with this. So we'll say dou loss function divided by, because it's impacted by this, dou HI of L multiplied by dou HI of L divided by, and this is impacted by this, dou A of IL. And you know how is this impacted? So you know that this basically was activation of this. So I can directly write, so if I just replace it, so this was when we applied F onto this AIL. So I can replace whole of this by f dash of AI of L. So this is error at Lth layer. So this is the term I defined, error at Lth layer. And this over here is derivative of the function. So this is derivative with respect to this AI of activation function, whatever activation function you are using, and this, you know what it is. So this is loss function, and this is the Lth layer output of the single. So this is in vector, this is in element wise form. And the one that we wrote over here, so rather this should not have been written in I. So this over here is vector form. And this is not just multiplication over here, I named it as Hadamard multiplication. So this is called as Hadamard multiplication. Everybody clear so far? How many of you understood this? People who are present in the previous lecture should be able to understand. Can I assume that you understood this? Now once we define this, now the point is we will have to do it for all the layers. Okay, before that I told you we should know some of the things. So if we have MSE loss, so you know what MSE loss is. So MSE loss basically is you have some prediction, and you have the actual value, ground truth, and you take square of this, and you do it for all the points. So if you have to do this, and you generally multiply this by 1 by 2, why? Because when you take derivative and this 2 comes down, so it cancels out. So if you have to compute dou L divided by dou HL, this, so for this, you know, for MSE loss, this is equal to HL minus Y. If you compute the derivative, so this is what you get. Okay, and now if you compute delta L of this, so if you compute delta L of this, you know what is this equal to? So this is equal to, again you have to remember this, so dou L divided by so this is dou L divided by dou HL and multiplied by this. So if you Now substitute the value. So what is this equal to? Dou L divided by dou HL multiplied by, so this is Hadamard multiplication, and this is f dash of AL. So this is what it is equal to. So dou L can be directly computed. So if you take derivative of this, so this is equal to this. So h of L minus y, and this is Hadamard multiplication of f dash of AL, and it depends whatever activation you have used over here. So you will again do that. Similarly for cross entropy, you also get the same thing. So for this is for MSE. So for MSE, so one thing that I haven't done is how to compute this derivative. That I think you can easily compute this derivative. So with respect to this MSE, you will be easily able to compute this and you will arrive at this result. So for MSE, this delta L is equal to this. In terms of binary, in terms of, let's suppose, cross entropy or softmax. So in terms of cross entropy or softmax, so this delta L, the error at the L clear, this is equal to HL minus Y. Okay, the only thing you have to compute this. So you have to compute dou L by dou H square, and then you have to take a derivative of this. And once you Hadamard multiply them, for MSE you will get this, for cross entropy you will get this. I think you will be able to do this. Once you do it at home, just pause the video over here in order to confirm these things, so that you are convinced that these are the values. Now we have to back propagate this error. Okay, if I take a small example in order to make you a little bit comfortable by just removing the mathematics part. So previously I told you, if you have, let's suppose, 1, 2 and 3 neurons, something of this sort. So you had one, let's make only 2 neurons. So you had loss function over here. So you had loss, this was computed, loss was computed somehow. So we call that L. So we said, how is this L computed? So this L is computed by HL. Okay, HL, on that you apply, let's suppose, something output activation or something of that sort, and you get this. And before this, how do we get this? You get this because this, we applied activation function on HL, AL. So we got this. But how was this AL computed? This AL was computed from 3 things. So this AL was computed by WL minus 1 or WL, sorry. So I'll write it over here, 1 and 2. So these are our 2 neurons, and this is our loss. And how do we compute this? So we had this WL, and then we had this HL minus 1, and we had this BL. So this is how it was computed. And how did we compute this HL? So this HL minus 1 was computed from AL minus 1. And you know how this AL minus 1 was computed? Again by 3 things. WL minus 1, HL minus 2, and BL minus 1. This is how it was computed, and this was called as a computational graph. If you remember from the previous lecture, this is what we named as computational graph. We said, we are saying, okay, how do we compute this loss? So we are computing this loss from basically y dash. So we get, from this we get y prime, and or we can write y hat. So we had some ground truth. So based on this, we compute some loss, and now we are seeing nudging the loss. We're saying, okay, what happened to this loss? I want to decrease the loss. So I'm trying to get this. I'm trying, okay, how can I improve the prediction? So I can improve prediction if I do something with HL. So how can I do something with HL? I'll have to do something with AL actually. I'll have to nudge values of AL. So how can I nudge values of AL? I'll have to do something with these 3 things. So here I can directly nudge these values. These 2 values I can directly nudge. I can make some change in these weights and biases. But for this HL minus 1, I again have to go back. Okay, I'll have to nudge values WL minus 1, and then with this HL minus 2 and BL minus 1. So these values, and I can directly change weights and biases there. And there we saw that. So by changing these weights and biases, we somehow impact this loss function, and that is the only way to make this loss better or worse. So you have to somehow have control over these weights and biases, because everything, if you see, is somehow connected to these weights and biases. And now we are at the last layer. So if you see, so this is what I want to explain over here. So we're in the last layer. So you have, if you just have 1 neuron, suppose. So you have some cost function or loss function associated with this, and what you will do is you will say, okay, how is this being impacted by this? Okay, you will use chain rule. You will say, I have to compute, let's suppose here there is some parameter AI. Okay, dou L by dou AI. So this is what basically I am computing. So that's why I call it error. So error at any layer. If I have some parameter AI, pre-activation at any layer. So what I'm saying is I have to compute that thing. Okay, how do I compute that? So I coming from loss, because loss is getting impacted by this. It's getting impacted by this. Let's say it's getting impacted by this. That's why I'm using the chain rule. Okay, so here we saw that on the last only on this layer. So if I have to compute some dou L by dou A, and we defined that by using this error. So this is one short justification which we discussed in detail in the previous lecture, and now we will see what will we do for the other layers. So now we have these layers. Now we have k is equal to L minus 1 comma L minus 2 and so on till first layer, because we computed this del L was computed for we computed it for Lth layer. And now why did we compute it? Because it eased our calculations out. Let's do that. So now you have this dou I of k. If this k is equal to L minus 1, L minus 2, because you know about L. So if you take it element wise now, so this is for kth layer. So how can you do this? So you have to do this something of this sort. So you will take the bigger matrix, okay, and the matrix will be W k plus 1. So that matrix, the matrix that is in between that, and you will take, let's suppose, and you will fix that one row. You will fix that Lth row, because you let's suppose you are talking about some point. You will fix one row, and you will say Let's suppose we'll say use some different notations where I don't overwrite this notation ij. So now you have this wk minus 1. Let's say you will say from L1 to say how many, whatever there are, k plus 1. So because we assume that after that k plus 1 neurons are there. So you take this and then you fix one. Let's suppose you fix this I, because you are computing this I and you will fix this. So del I, you will fix I and you will narrate this. So you are fixing I and you are taking the whole of that vector. And then what you are trying to do is plus this bias also. So if you see over here, so you can also take bias, or you can without taking bias if you take consideration, and then you have to multiply this with delta L. So whatever came before this, the error k plus 1. Okay, let me justify this, and then we have one more term that is multiplied by whatever was the activation f dash of a I of L. Okay, so this is for all the layers. So let me justify this. So what I'm trying to do over here, so as not mess up the notation, let me just check the notation if notations are correct, so that I should not give any wrong explanation. Right. So what I'm trying to do over here is, now you have this vector, you have some value computed. If you talk about one neuron, suppose, if you talk about this, so this might be getting impacted by different ways. You are computing something of this sort, and it might be connected to a lot of neurons. It might be connected to this, it might be connected to and a lot of these things. Okay. So what I'm trying to now do is, so I'm trying to see what is the how I can compute the gradient of this. So how, because I'm adding this, if you remember that reflection on calculus we said that okay, I'll have to add all these derivatives. That's what I'm doing. So for this neuron, let's consider this single neuron. So how to compute this? So you know that it will have some k plus 1 because it is coming in k plus 1th layer. So this is kth layer. If you see, this is at k plus 1. So it will have some del associated with it. So this neuron will have some del associated with it. Okay, so there will be this del k plus 1 will be associated with all these neurons. Okay, and if we just talk about single neuron, so talk about a single neuron, and you take that whole vector, and then you take one row and you take the multiplication of those things. So that's what I am doing. So you had this big matrix, and you take one vector in that, and then you multiply it so as to get this one value. Okay, if you see in the previous, that's what I assumed over here. So if you see one node over here, so one node, that's how it was computed. So if you see one node, because it was impacted only by one node, let's talk about this node. So it was getting impacted by this, and this was getting impacted by this. So for one node, if you remember, for Lth layer, this is how we wrote it. So we said dou L is equal, so this is loss function by this, and then activation of this. So again, I'm doing the same thing over here. What I'm saying is, so you have this. So how to, this is activation, leave it apart. So activation already is there because activation was applied in order to get there. But I'm trying to justify this value over here, basically the other value. So you had two terms in here. You had dou L divided by something. So you had loss function by something and multiplied by, and you had this activation. So activation is pretty clear because we are having activation function by the help of chain rule. We'll get this, and you have computed this for the next layer. So this was already computed for this. Now we are using it. So we are using it for this. We are computing for this, and then this, and we are adding it all together. And we are adding it all together. If you see, we are applying summation on this. So if you remember reflection on calculus, where we saw that if you have one node and if you have it's branching towards multiple nodes, so in order to compute its derivative, so what we try to do is, so we compute derivative of this, and this. We take all these and add it over here. So that's what we are doing. So we are computing for one. If you take just ith neuron, so this is for this. So if we take ith, and if you let's suppose take for I neuron, so this is ith neuron, and if you take L, so L will range from 1, 2 till k and k minus 1. So how many neurons here are? So this k plus 1 which I wrote, and k plus 1. So the number of neurons at this k plus 1 layer. So this will go till there. First it will compute with this. It will compute gradient of this, and then it will compute gradient of this. Then it will compute gradient of this. Then I'll add all these gradients. So that is what this term is telling you. So if you see this term, so if you just say L is equal to 1, so it is talking about this neuron. It's telling you the gradient of this neuron, and gradient of this neuron is when L is equal to 2. When L is 3, it's talking gradient of this neuron. So when you add these things together, okay, and then you get this whole gradient, and then you already also know that it was also multiplied by activation function. So by the help of chain rule, so this is the activation function. So is it clear for everyone? So if you see this example, the example that we were taking earlier, so we're considering there is one node and it's impacting one node. Okay, let's suppose we had this loss function, we're saying it's impacting this and it's impacting this. And now you know in a network there is a lot of nodes are there. Let's suppose one node is connected to multiple nodes like this. Okay, in order to now do this, because you know from the basic calculus, you know that you have to add these derivatives all together. So if you have to compute gradient of one thing, if you have to compute derivative of this, you have to compute derivative of these things and then add these things together. That is pretty much clear for you people. And now introduce this notation, this delta L, this is the error. So this is the error at every layer. So on Lth layer, so if you see this error at Lth layer, so that is equal to take the loss function and compute, because at the Lth layer you have HL. So compute the derivative of this. Basically you want to compute how is this delta L defined. So delta L basically tells you compute this. So you have to compute dou L divided by dou AL. So this is what you have to compute. This is what error is. So loss function with respect to this aggregation function. This is what you have to compute. So we are saying, okay, this dou L, because this AL comes from HL. So that's what I have written over here. So dou L divided by dou HL. And then I'm saying, because we applied activation onto this. So if I can write this, so I can write it like this. Okay, if I remove this, so I can write it multiplied by dou HL by dou AL. But you know what is the value of HL? HL, we got it from f of AL, activation on this L. And you know, I can write it directly like derivative of this. I can say this is the derivative of f of AL. This is how we define the error. So now you define this at Lth layer, and now you are trying to propagate backwards. So you are saying, okay, let me now do for other layers. So you have this k is equal L minus 1, L minus 2, L minus till 1, L minus 3 till 1. So let's suppose we'll consider this. So this right now we are doing it for one element. So if I have to compute error of let's suppose that delta k vector, so that again will be a vector, okay, and I have to compute its ith entity. So what's the ith entry equal to? So what I'll do is, I'll say take a bigger matrix, take the k plus 1th matrix. That's what we have been doing. Take that matrix and then do one thing, fix this ith component, fix the ith component. That's why I said it should be written in reverse. So once we are fixing the ith component, so we are saying, okay, fix the ith component in that and make this L vary. So make the L vary. So basically what you will get one value out of that. Okay. So when you are getting one value out of that matrix, and then basically you are trying to compute derivative of at this, you are computing error with this at this value. So when you compute this and you multiply it with what came before it, because there will be error vector with that. So error vector will be delta k plus 1. So delta L, if you see here, it will be associated with this vector. So if you say L is equal to 1, so for this this will be delta 1 of k plus 1. So with this associated node. So if you take only this term, so the term that I am writing over here, so this is associated with one neuron. So this is basically the value that is at one neuron, derivative at one neuron, and this is derivative at second neuron and third neuron, and then I am adding it up because I know how calculus works. So I am adding these things up. That's why I am writing summation of this. And you know that this f of IAL, this we got from chain rule because we also applied activation on that, and we got this. And you know that if you unbox this term, so this term is not just one term. So you know that this again is composed of many terms. So how I can write this? So this basically was equal to dou. So this was some k plus 1. So usually I'll not write it directly as the loss function. So we'll say, so this is by loss divided by dou a k plus 1. Okay, this is how it is equal to. And now you know that this also can be unboxed by using chain rule. So this is dou L divided by dou. How do we arrive at this k plus 1? By h k plus 1. So I can write dou L divided by dou h k plus 1 multiplied by dou h k plus 1 divided by dou a k plus 1. So again, if you see, this is the unboxed version. So I can multiply this thing with this. Okay, I can keep on doing this. And if I have to like do for other terms, so that's why I wrote k over here. Now you can choose this k to be L minus 5, L minus 2 till 1, and you can repeatedly use this equation to compute this delta k. And now let's do the shape check. So let's do now in the vector form. So this was for one element. So this was for just one node. Okay, now I have to compute this. My network is something of this sort. So my network is something like this. So everything is connected with everything. So we have fully connected network, something of this. So I showed you how to compute for this and this 3, let's suppose. So this is one element that I did here, this delta ik. So now I have to compute for all of this. I have to do it in vector form. So how to do it in vector form? Pretty easy. So this delta k, this is equal to, now I won't be using directly summation because I have the whole I have this whole thing with me. So I'll say w, so this is my w, and k plus 1, this is the whole matrix with me, and then I'll put the transpose of that. So I'll transpose that and then multiply it with this delta k plus 1, and then do the Hadamard product of this a, this is k. Have I written this ak over here? Yes, I think this is L mistakenly, so this should be k. Okay, because this is the activation of ith layer in that kth layer. So you have the kth layer and you have this ith element in there. Okay, this over here which I wrote, so this, if you see, so this, if you see, is in the vector. This is element wise form, element wise. So what do we do is, we have one element, we did it for one per element, but you know that there you have the whole layer. So you have the whole layer with you. So this is for the whole layer. You came up with this delta k. So actually the layers were like this. So you had layers something of this sort, 1, 2, something of this, and then dot dot dot, and then you had this vector, this and this. Suppose you had a vector associated with this. So this is delta, suppose k plus 1. So this is k plus 1th layer. So you have for all this. So this is delta k plus 1, 1, delta k plus 2, delta k plus 1, 2, delta k plus 1, 3. This is the whole vector that you have associated with this. And now in order to compute for this, so we computed for this. So we have to sum all of these first, and then plus we have to sum all of these things, and then plus we have to sum all of these things for all these delta k's. So that's what I wrote, the summation over here. So this is just for one element. So in order to put for all these things together, you see that this vector multiplication. If you expand this, you will again see you will get this form. So you'll get this matrix. You will get double you'll get this, and then you'll have this summation form back if you see this. So if you just consider it for one element, but if you consider for all the elements, so let's do some checking. Let's do some dimension check. All the dimensions same. So you know that, let's suppose we have this wk plus 1 transpose. Okay, so this will be whatever the number of neurons were in the k plus 1th layer and multiplied by, so this will be n cross n k. So this is the number of neurons at k plus 1 and number of neurons at k. You know that how this matrix is constructed. Okay, so this is so I think this is transpose. Now it will be, so if you write wk plus 1, so this, the dimension of this is equal to number of neurons at k plus 1 cross number of neurons at kth layer. So now we want to transpose it, so you will get the dimensions of this will be equal to nk cross nk plus 1. So I think these are the dimensions for this. And now the second thing that we have to, this delta k plus 1. So what will be this delta k plus 1? This is simple, it will be a vector. So what will this vector be? So it will have nk plus 1 cross 1 cross 1. So number of neurons at k plus 1th layer, so that's what we are computing, cross 1. And then if we multiply these two things together, so that's what we are doing over here. Multiply these two things together, so what will we get? So you will get n of k cross nk plus 1 and then multiplied nk plus 1 cross 1, and you know that this will be equal to nk cross 1. So that is actually correct because number of neurons at the kth layer. So this is the result, and I think you people got it. So how many of you understood this discussion, the thing that I wrote on the screen? Now we have to discuss the core stuff. The core stuff basically was we have to compute derivative of this with respect to some weight, or derivative of this with respect to some bias. This is what we have to compute. We can write it ij some value, and this is some bki. So this is what we compute if we do it element wise. So this is what we have to compute. So if somebody tells you now, can you give me this? So you have to compute dou L. So if you now assuming that you know this delta k, you know the error now. Okay. So computing this element wise, dou L divided by dou wi j k. So this is what we have to do. So what we will do is, so we will say dou k of I. So whatever is the error. Okay. And after that you had this aggregate and you applied this hk. You had this hk before this. After you have this, so you do h j of and this k minus 1, because k minus 1 is the layer where you had, let's suppose you have this error weight now. So once you have this, so the only point that you have to compute is respect with some weight. Suppose it had some weight over here. So one weight wij, and it is, let's suppose, at kth layer. Consider this we have to compute. Now you know that we have the error at this place. So we have error ki. So you know how to compute the error. So error was with respect to ai. Okay. So you know that we had hl came from al, and this al basically came from w. So this came from, if you see, from the previous layer. Okay, so this is what we came from. So I think I should not write a, I should write k's rather. So make it clear. So if we had hk, so how do we arrive at hk? So we arrived at hk by applying activation function on ak. So how do we arrive at ak? The graph, if you can remember it. So this. So hl, this is, so you get it from hl minus 1. So that's what I did here. So I got it. This what I got it from hk. This I got from ak. So how did I reach at ak? So ak I reached it by h k minus 1, and then you have weights, and then you have bias, something of this sort. So this is what we saw in the graph, and now you know this error. Okay, so you know a lot of stuff. You have to compute, let's say, with respect to this weight. You had some weights over here, but you know how do you reach here? So you had some loss over here, and you had computed this delta k. So till here this is done. So you have computed everything till here, till with respect to this ak. That is what this error is. Okay, so if you see, so this is what this error is. And okay, this is also impact. So if you now want to see how is this w impacted, so you also have to add this. If you see this wj, you have to take one element and you have to see this k minus 1, and this is what how you can compute it. If you understood this whole thing, I'll just erase it, and you have to remember this. Doing it once the hard way, we'll do it easy way, but that's called autograd though, but you have to get to know it. So you have this weight vector. If you know this weight comes in somehow, and you know this thing already, and you just have to multiply this hj k minus 1, and you will get the derivative of loss function with respect to that weight. But assuming that you know all of this, and you know to compute this, you have to keep on computing the gradients till this point. And similarly, now if you have to write in the vector form, again, let's say this is element wise form. So this is element wise. So again, do the same thing with bias. So if you know the bias also, so bias also follows the same thing that I made diagram. So this is the bias. So bi of k, one bias. So now you know that for bias, everything is constant. When you take derivative, with respect to this. So you know how is why this hjk plus 1, because actually it should have been whole equation, it should have been the whole function, but you know that it was w k hk minus 1, something of this sort, where we got that term. I think I should keep that diagram so as to make you understand thoroughly. So you had one neuron and then other neuron, okay, and let's suppose this is what we were doing, and you had delta k. Suppose we had, this is at the kth layer, so this is k, and this is k plus 1, and this is k plus 1, and this is your k. Again, making you understand this. So now we have to compute dou L, because you know that how did we get over here? So we got, let's suppose if we have a neuron, so this we got, suppose hk we got it over here. So hk we got from ak actually. So ak was, we operated on ak and we got this hk. How did we got this ak? So this ak was, we got from three things. So we got hk minus 1, wk, and bk. This is how we got it. This is how we got this ak. And now this ak can be written, you know, by forward pass. ak is equal to wk hk minus 1 plus bk. So when you take derivative of this with respect to this, let's suppose hk minus 1. So you will see that this will go to 0 and it will, this will go to 1. You will be remaining with this. That's why I wrote this hk minus 1 over here. If you see this, again see this, hk we got it from ak we got it from these three things. Okay, so when you take derivative of this with respect to whole of this term with respect to hk, okay, this is what we had to do. So when we took this derivative, so what happened? So this partial derivative, so this is constant, so this will go to 0. And when you take derivative of this thing by hk minus 1, so you will be left with this hk minus 1 only. Okay, so if you see, we're taking this is the derivative we have to take with respect to wk, and this thing will go to 1 and you will be left with only this thing. So it is something of this. If you have 2x, if you take derivative with respect to x, you will be left with 2. So that is what we did over here, because we had derivative of L with respect to this w vector. So I said, okay, this derivative is equal to, take this delta I and multiply it by, then ak. Actually derivative should have been, we should take derivative of a of this ak, but you know this ak is dependent on these three things, and when you take partial derivative of that with respect to this weight, so you know this thing will go to 0, and among these two things only this hk minus 1 will be left. How many of you are on the same page? So if you see, this was dou L by dou ik. So we saw this from this diagram. We are taking derivative of, let's suppose this, we want to take derivative of this, and with respect to, let's suppose, this weight. So we had this weight over here, but you know how to take derivative of this. So if you expand this equation ak, so ak is equal to wk hk minus 1 plus bk. So when you take derivative of this with respect to wk, so this will go to 0 because you're taking partial derivative, and among this it will be left with wk hk minus 1. So you will get this one as 1 and you will say hk minus 1. So that's what I wrote over here. So that is what I wrote over here, if you see this, and you know what this error is. So this is delta ik, it was already computed. And now if you understood this, if we have to compute dou L by dou bik, okay, so bias k at the layer k, we have some bias vector, and I want to take it's one component, one element. So what will this be equal to? So again expand this equation, so you'll be left with delta I, and then if you expand this whole thing, if you expand again this, if you expand ak will be equal to wk hk minus 1 plus b, but when you take derivative with respect to b, so this whole thing will be going to 0, and this thing over here will be equal to 1. So that's why we are left with only this. So this is derivative with respect to with respect to weights, and this is derivative with respect to biases. And if I write it in the element wise, so how I can write it element wise? So dou L by dou wk, you will not take derivative element by element, so you will take it on the whole matrix. So how you can do that? So you'll take whole of this, and then you'll say hk minus 1 transpose. Okay, that's what we wrote over here, rather j. So here I removed that j, and this is with respect to weights, and dou L by dou bk for all the bias in the kth layer. So you will be leaving with you'll be left with this. So these two over here are the important step. If you understood this error, if you understood all of these terms, so this is your backpropagation. So this is backpropagation. Now you can give me any layer, I can give you the you can repeatedly apply these things, and you will get basically the value of this. And after this, what you will get? You will get something of this sort. You will get dou L by dou w1, okay, and you will get dou L by dou w2, dou L by dou w3, and so on, dou L by b1. So this is bias at layer 1, dou L by dou b2, and so on. Now if you got these things, now you will apply gradient descent. So what you will do is, you will take all these values, and you will take these matrices w1, w2, w2, w3, and so on, bias 1, bias 2, bias 3, and then you will apply gradient descent. You will make updations on these updations, So how, and this can be, this we generally write as delta. So we write it like this, something of, and there will be complex notations here and there, but you can use these things. So this, again, all of these things will be used to update these values. Okay, this over here is backpropagation for you. How many of you understood backpropagation? Again, I'll tell you, just summarizing it, maybe just couple of minutes. So what we defined an error term first. We said, let's consider an error term. Error was defined something of this sort. So error was defined like this. So you had this dou L by dou A. So if you see, so this is dou L by dou Al. So this was the Lth layer, final layer. So this is how we defined the error. There are a lot of things. So this over here, if you see, this is how we defined the error. So we had to compute dou L by dou theta. You know, these are the parameters. And now we defined one term that was called as error term, error at kth layer. So this was the error at kth layer, but for one element. So we said dou L by dou AKI. Okay, so this was ith point or ith element or the kth layer. So this is how we defined it. So and for all the layer, we'll say delta of k. So this is delta k is equal dou L by dou AK. So this is defined as error at kth layer. We defined this term so as to represent these symbols succinctly. Now again, now if you see at Lth layer, so Lth layer we had AL and we had HL. So now if you take about one element, so if you have to compute this dou L by dou AL, so how to compute that? So you will take dou L because this is impacted by HL. So what came before it? So that's what we wrote over here. Okay, so we wrote dou L. So this is computed by HL, and then you know how did we got HL? So we got HL basically by applying activation on this. So once we apply, we can take derivative of that by using chain rule. So this is what was for the one element, and this is for in the vector form. So delta L is equal dou L by dou HL, and this is Hadamard multiply. Hadamard basically means you take one element, multiply it here, one element, multiply it here. Okay, and you take it, and this is the derivative. With the derivative of the activation function. So this is how this delta L was defined. After we have this, we have some loss function. So I told you if you have loss function, so these are the common things that you have to compute. So for the MSC loss, this dou L by dou HL is equal to this, and so delta L at that point is equal to this. So for softmax and cross entropy, so this you can verify. So the value is the value of delta L is equal to this. And now once you have this, so you have to compute for L minus 1, L minus 2 till first layer. So I said, okay, let's name that as K. Okay, del K. Let's compute the error at all the layers. Okay, why do I want to compute error at all the layers? Because I want to compute the derivative of loss with respect to weights and biases. Again, I introduced this notation. Delta Ik is equal to, so I said now you have to do it for one element. So this is for one neuron. So one neuron, and it is connected to multiple neurons. So when it's connected to multiple, you sum these things up. That's what we added all these things up, and then you had also activation over here. In order to write in vector form, so we did delta K. So we took a transpose of that weight matrix, and you multiplied with the error vector that you already computed in the previous step. So for delta K minus 1, and you perform Hadamard multiplication. So once you have these things, so we also perform dimension check in order to see was this correct, and we got that dimensions were correct. And now we also did it for this was the element Y. If you now we have this delta K. Now we have to do what is this dou L by dou Ijk. That means what is the derivative of loss? How is this derivative getting impacted by particular weight or by particular bias? So we said, okay, we have the weight vector over there, we have the error vector over there. So you have this error. Okay, so how did we got this error? So we got this because previously we have this HK minus 1. So you had this HK minus 1 on that. So this is how it was. We made a diagram. So this AK, it was impacted by this WK, BK, and HK minus 1. Okay, so now we have to compute with this respect to this. So how did we got this? And you can clearly see with respect to W, it is HK minus 1. With respect to B, it is 1. So that is how we got this error vector only. Okay, so this was element wise over here. Now we know how to perform how to perform backpropagation element wise. So we can write it in the vector notation. So in the vector notation, this is how it is written. So this is backpropagation for you. So this is with respect to weights. So this is for weights, and this is for biases. So now you should be able to do the backpropagation by hand. So usually what we do, so this is for one sample. So this is done for one sample. So you have one sample, so you do these things. Okay, we'll go to after that mini batch. So in the mini batch, what we do is we do not have now. We will not do for every point. So we will just shuffle the batch. So this thing actually has to be done for all the points, and then all these gradients have to be added. So let's suppose for this we'll get gradient with respect to W1, gradient with respect to this. So you do it for all points. Let's suppose you have 1 million points. Say you have 1 million points. So you will compute this 1 million times. Okay, and then compute the gradient for all the points, compute the gradient for W1, W2 with respect to all the points. So after that, you will average these things up. You will add all these gradients and average it out. But you know, performing forward pass and then perform this backward pass just for one point is quite heavy. So if you do for 1 million points, it will take a lot of time. So what we do is, we do this mini batch. So we take a mini batch. So in that mini batch, let's suppose you have 1 million points. So you give them a really good shuffle, you shuffle them up, and then you take a batch size of, let's say, 64, you take just 64 points, assuming that by the law of large numbers, you'll say that I am sampling uniformly these 64 points, so they somehow represent the population, so they will give me some gradient vector. So I'll compute with 1 point, I'll do this pass, forward pass, backward pass, and I'll keep on computing these gradients, and then after 64 points, I'll add these and average the gradient vectors. Okay, I'll average whole gradient. Basic gradient means the derivative of all these vectors, and then I'll make these nudges. Okay, so I have to make adjustments, which I was telling you in this gradient descent. I'll not make adjustments every point. After every point, I'll not make the adjustment. So that this is, you will perform this gradient descent directly like this. But this is not what you do. So usually in real world, what you do is, so you have not with 1 million points. So you will take just maybe a mini batch, 64, 32, 128 points, and after that you will compute gradient of the network with respect to those points, and you will add them up, take average, and you will get this. So basically what you get is, so I told you this is written by delta of this. So if you write delta of k plus 1, so how do you write it? So this is W k plus 1 transpose delta k plus 1, if I write it like this, and this is f of ak. Okay, so here these are my actives, so I can write this. So gradient over batch things is, so you have to compute dou L by dou Wk. So this is what you have to compute. So this will be equal to average, take average of all these things, and take this, take hk minus 1. After, I'm just writing the capital letters to show you for all the points. This is for all the whole points. So this is hk minus 1. And usually if I write small hk, that means for one layer, for 1 point. Now I'm writing capital kh, so that this basically means for many points. This is not for just 1 point, this is for more points. Okay, and this is with respect to weights, and this is with respect to bk. This is 1 by m. Again, take m points and summation of delta I, and I think this is t. I don't want to mess up the notation, I am being careful. So this is t goes from 1 to m. So these many points. So this is for weights, and this is for biases. So here if you see what is this hk, so this hk is activation for all samples. So activation for all samples. So there we were seeing activation for one sample when you wrote small h. So this ak, this is pre-activation. So why did I write that ak? So I wrote it somewhere in ak. Yeah, this is pre-activation for all samples. So this is again pre-activation for all samples, for all m samples. That's why I wrote them in capital letters. So okay, this delta k. So this again, if you see, I was writing small delta. I was writing delta k like this, delta k plus 1 or k, something of this sort. I was writing delta k. So this was with respect to 1 point. This is with respect to all the samples. Okay, and you can compute this. So hk, if you see, hk will be the dimension of this will be r nk cross m. Usually we had just one vector. If I have told you this hk, this delta k, all of these are one vectors, but now you have m sample. So now you have, this is the dimensions. So again, similarly, ak, small ak was just one vector at one layer. So now this will be a matrix. So this will be r nk cross m. So this is pre-activation. This is activation for all samples. This is pre-activation for all samples. Should I write it? Activation for all samples. Basically m samples. If you use m samples, this is pre-activation for all samples, and then you have this delta k. Okay, so if you see this delta k, this again was a vector, but in this it will be a matrix. So this again will be r n cross k multiplied by 1 because of these m number of samples. So this is what we generally do. So this is called as mini batching. So we do mini batch. Why? Because we cannot do it point wise, or we cannot do this for all the points once, and then it take a lot of time. We generally just shuffle this, give it a really good shuffle, and just take 64 or maybe some 32 samples, and then assume that they'll also point to the same direction, in which if we compute the all, but it sometimes is wrong though, it's not correct, but we assume that because we are shuffling them and we are taking every time we are randomly sampling this batch, so we assume that at average it will be the right direction that we want.